Welcome to Chapter 2 on water. In this chapter, we're going to discuss two main categories of information. The first is on the physical properties of water. This includes the polarity and intermolecular forces between water molecules, the interactions of hydrophilic and hydrophobic molecules in water, as well as the movement of molecules in a solution. In the next video, we'll discuss the chemical properties of water. So let's start out by recalling what you've learned previously about what does a water molecule look like. So please take a moment now, pause the video, and just draw what your recollection of what a water molecule looks like. It can be a Lewis structure, it can be anything you recall. And once you've done that, we'll move on to the next slide. So hopefully the molecule that you drew looks a little bit like this molecule here on the screen. So this molecule depicts a water molecule. You have a central oxygen atom surrounded by two hydrogen atoms. They are covalently bonded, and the angle between the two hydrogen atoms is 104.5 degrees. This cloud surrounding the water molecule represents the van der Waals envelope. This depicts the shape and size of the electron cloud that surrounds the whole molecule. The oxygen has slightly larger van der Waals radius than the two hydrogen atoms, and the bond length is almost 1 angstrom. So that sort of depicts the shape of the water molecule on the left. On the right, we have an image that looks a little bit like the one on the left, but this one depicts the electrons. So the central oxygen has 6 valence electrons. 4 of them are located in the 2 lone pairs that you see here. The other 2 are participating in the covalent bonds with hydrogen. And you can see that the molecule is sp3 hybridized, so you have these, that makes it have this particular shape. And these electrons that are participating in bonds, as well as the ones in the lone pair, can help us start to think about the charges that are within water molecules that help them to interact with each other. And the way we can start to think about how the charges are distributed within the water molecule is by considering electronegativity. So this chart is a periodic table that depicts all of the elements, and they're color-coded by their electronegativity. So you can see on the right side of the chart, you have this concentration of more highly electronegative molecules. And then as we move towards the left side, we can see these less electronegative elements. And the differences between the electronegativity of particular atoms that are made from different elements can determine how they interact with one another. So you can see in particular for water, the oxygen is quite electronegative in this red color, and the hydrogen in yellow is a little bit less electronegative. So when we talk about the charges that are within a water molecule and the electronegativity differences in general are between any 2 elements, that can tell us the type of bonds that might form between those 2 atoms. So if we have a small electronegativity difference of less than 0.5, this is going to give us a non-polar covalent bond. And the molecule with these types of non-polar covalent bonds will have very few charges within that molecule. With a sort of intermediate difference in electronegativity between 1/2 and 1.9, here we still have a bond that's covalent, but the bond is polar because the electronegativity interactions between the 2 different atoms allows the bond to have a more positive end and a more negative end, hence it is polar. So you end up with these partial charges in the molecule. Finally, if you have a very large electronegativity difference between the 2 atoms, then you will end up with an ionic bond. So in a molecule that has ionic bonds, you will see that the atoms have full charges on them. So they're either positively or negatively charged. And again, once we consider water, which is the topic of our conversation in this video, we have hydrogen and oxygen atoms. Oxygen has an electronegativity of 3.44 and hydrogen has an electronegativity of 2.2, which puts us in this intermediate type of electronegativity difference, giving us a polar covalent bond within the water molecule, and which gives the molecule itself partial positive and negative charges. So let's talk about all the different types of bonds that we tend to see in biomolecules. In this slide, they are ordered from essentially strongest to weakest. So if we start with our 2 in the top, we have covalent bonds and ionic bonds. These types of bonds are sort of interchangeable. Some covalent bonds are stronger than ionic bonds, some are weaker, and the other way around. So you can sort of overall consider both of them to be about the same in terms of the strength of those types of bonds. So to define them, which you probably already know, covalent bonds are intramolecular bonds within a molecule in which the 2 atoms share electrons to create a bond. And this is in contrast to the ionic bond. Ionic bonds can be either intra or intermolecular, so either among 2 different molecules or within the same molecule, and this is between fully charged atoms. So these bonds, like I just said, are considered approximately equivalent in strength. The rest of the types of bonds and forces that we see on this slide are considered intermolecular forces, or IMF. And we can again proceed from, instead of proceeding from strongest to weakest, going down the slide, we're actually going to start at the bottom and work our way up. So at the bottom, we have our van der Waals or London dispersion forces. So van der Waals are often abbreviated VDW. London dispersion forces are often abbreviated LDF. And these are the types of intermolecular forces in between 2 molecules. And they can happen between any 2 molecules, but they're considered most important among nonpolar molecules. These are the only types of forces that nonpolar molecules can make with one another. And they happen because of the random distribution of electrons within the electron cloud in one particular area. So there can be very temporary, slightly positive or slightly negative areas of that molecule that can then interact with those very temporary, slightly positive or slightly negative areas in another molecule. And that can happen even in a bond that's overall, in general, nonpolar. This is very short-lived and very weak. The larger the molecule, the stronger these forces can be, but in general, they're considered the weakest type of force. And that brings us up by 1 to what's labeled E here, the dipole-induced dipole. So this is an intermolecular force that is between 1 polar molecule and 1 nonpolar molecule. So in this case, the partial charge in the polar molecule can induce an opposite charge in the nonpolar molecule. So for example, the negative side of the polar molecule might repel some electrons in the nonpolar molecule, thus creating a sort of temporary partial positive and partial negative interaction with each other. Going up by 1, now we have the dipole-dipole force. This is an intermolecular force between 2 polar molecules, and this is a little bit stronger. So this is when 2 polar molecules, the partially positive side of one interacts with the partially negative side of another. And this is a relatively strong intermolecular force. And finally, the strongest intermolecular force that we're going to consider today is the hydrogen bond. And this is actually a specific subtype of the dipole-dipole force. So a hydrogen bond is the interaction in between a hydrogen that is bound to either in nitrogen, an oxygen, or a fluorine, and that hydrogen is bonded to a lone pair of electrons that are located on a separate nitrogen, oxygen, or fluorine. So again, we're working here with water, so the hydrogens on the water are covalently bonded to an oxygen. So in this case, you'd have an attached to an O on one molecule, one water molecule. The other water molecule contains that central oxygen. And so then you can form a hydrogen bond in between the hydrogen of one water molecule and the central oxygen of a separate water molecule. So the other bonds that we want to consider within water, aside from that hydrogen bond, which is a type of dipole-dipole bond, are the covalent bonds within that intramolecular bond in between the hydrogen and the oxygen, as well as the van der Waals or London dispersion forces, which are very weak forces that occur in every type of molecule, including water. So that brings us to how water molecules might interact with one another in a solution. So on the left-hand figure in this slide, we can see two water molecules and the hydrogen bond that helps to bond the two of them to each other. So on the top, you have this hydrogen. It's covalently bonded to an oxygen. Then we have this hydrogen bond that connects to the lone pair on the central oxygen of another water molecule. And as is pretty apparent in this figure, each water molecule has a couple of lone pairs, it has a couple of hydrogens, and so you can start imagining that, especially in 3 dimensions, water molecules can start to form multiple hydrogen bonds with other water molecules. So in, a cup of water, you can have several hydrogen bonds that are attaching together multiple different water molecules. When you think about ice, the central figure in this slide, ice is a very orderly arrangement of water molecules. Each water molecule in ice forms 4 hydrogen bonds, which is the sort of maximum number of hydrogen bonds, and this helps it make this very rigid, orderly shape that is solid. When you think about and I just want to add, in this picture, only, I believe, 3, depending on how you look at it, it's hard to see all 4 hydrogen bonds from each water molecule, just because it's really hard to depict 3D on a flat surface here. But keep in mind that ice is the most sort of highly crystalline, orderly structure of water. Then on the right-hand side, we can imagine what liquid water might look like. So liquid water, there's a little bit more freedom of movement between the water molecules. They're perhaps breaking and reforming hydrogen bonds with different neighbors of different water molecules that are surrounding them. And it's a little bit less orderly than the structure of ice. So that brings us to, I want to show you a little YouTube video. I'm posting the link here in the slides in case for whatever reason you can't see it that well in this video. And that sort of shows a little bit of a better picture of what liquid water might look like on the molecular level. So let's bring that up here. And so as you can see, the water molecules, within each molecule, the hydrogen-oxygen covalent bonds are sort of vibrating and wiggling. They're getting the hydrogens are getting, dragged away from the covalently bound oxygen by the oxygens on their neighboring water molecules that are forming these hydrogen bonds that are shown in purple. Some of the hydrogen bonds are breaking and reforming as the molecules move away from each other in space and toward each other in space. And so you can see that this structure is dynamic. It's not extremely rigid. It's not very orderly and crystalline. There's a lot of movement going on within liquid water. So let's go back to the slides. So that brings us to things we're going to have to consider in biochemistry, which are substances that are dissolved in water. So the first thing we're going to consider are hydrophilic substances that we dissolve in water. So at the top on the left, we have this example of a sodium ion. A sodium ion is positively charged, so it's going to be more attracted to the polar negative oxygen atoms within the water molecules, and that negative part of the polar bond the polar molecule will be attracted to the positive ionic substance and surround it and keep it dissolved in water. You sort of see the opposite of that with the chlorine ion on the bottom here. The chlorine ion is negatively charged, and so it's going to interact more closely with the positive side of that polar water molecule. Then if we consider on the right-hand side of the slide, we have several types of functional groups that we should be familiar with now, and we can see the types of hydrogen bonds that they form with water. So in part A of this figure, we have an example of an alcohol, which contains a hydroxyl group. So the hydrogen in the hydroxyl group is attached to an oxygen, which allows it to form a hydrogen bond with the lone pair on an oxygen within a water molecule. We also have the oxygen in that hydroxyl group, which has a lone pair that can interact with the hydrogen on a water molecule that is covalently bonded to an oxygen. So those are two different types of hydrogen bonds that can form between a hydroxyl group and water. In part B, we have a ketone. So we have this internal carbonyl with two R groups, that's a ketone. And the oxygen on the carbonyl has lone pairs that are able to interact with the hydrogens that are part of the water molecules that help to surround it and keep that part dissolved in water. In part C, we have another carbonyl group. This one is part of a carboxylic acid, or more specifically, a carboxylate ion. And so this carboxylate ion has two different oxygens, and each one of those has lone pairs, which once again form these hydrogen bonds with the hydrogens in water molecules. And our last example on the slide over here is a positively charged amine. This amine has three hydrogens, and like we mentioned in our criteria for the hydrogen bond, these hydrogens are covalently bonded to a nitrogen. So that allows them to form hydrogen bonds with the lone pairs on surrounding oxygens that are a part of the water in the surrounding solution. So these hydrophilic substances are able to sort of maybe easily form hydrogen bonds with water, and that helps them to dissolve fairly easily in water. This is in contrast to hydrophobic substances. Hydrophobic substances, like we mentioned, are nonpolar. They tend to only be able to interact with each other through more nonpolar forces, such as the van der Waals interactions. And so when you have a nonpolar solute that you put into water, water tends to, well, first of all, the nonpolar substance tends to interact with other nonpolar substances using those van der Waals forces, and so it will tend to sort of clump together with other nonpolar substances because it is not attracted to the polar dipoles within the water molecules. In addition to that, the water molecules will form an orderly cage surrounding the nonpolar solute to keep it contained, and this is sort of the lowest energy version of trying to keep everything in this container happy. So you can see a sort of example of this on the right of oil in water. So in part A, you sort of see these oil droplets that are dropped into water that are surrounded with these sort of dark blue cages of water molecules that help to keep the oil contained and to sort of hide it from the rest of the water in the solution. Over time, all of those oil droplets will actually sort of merge together, and this allows you to use fewer water molecules to make that cage surrounding it that allows it to hide from the other polar and charged parts of the solution. One real-life example of this are methane clathrates. Methane clathrates are found deep in the ocean under high pressure, where methane gas, just like that oil picture that we saw on the last slide, tends to clump together and is surrounded by these cages of water that are called methane clathrates. These could actually become a big problem with global warming. If that methane is ever able to escape and go into the atmosphere, it'll contribute to all of the problems we're already having in terms of greenhouse gases. So that sort of brings us to other types of biomolecules. So we've sort of discussed molecules that are only hydrophilic and only hydrophobic, but we can also have a lot of other biomolecules that are amphiphilic. Amphiphilic molecules have both a nonpolar and a polar region within the same molecule. So two examples that we have shown here are fatty acids. The top one on the top is palmitate, which contains 16 carbons, and the one on the bottom is oleate, which contains 18 carbons. So you can see they have this long hydrocarbon tail that's nonpolar, and then they have this polar head that contains a carboxylate ion. So fatty acids can be bonded to a glycerol molecule that has a polar head group, which in this case is a phosphate attached to a choline. And this is another really common biomolecule that has this sort of polar head region and a hydrophobic tail region that is amphiphilic and is a common part of, for example, cell membranes. So how do amphiphiles behave when they're interacting with water? So the top examples we had of just those free fatty acids, palmitate and oleate, based on some of the forces we've discussed before, the nonpolar tail regions, they're going to kind of clump together and hide in the middle. They can interact with each other through van der Waals forces. And those are going to sort of bring themselves all together and allow the polar head parts of the fatty acids that are charged, so the carboxylic acids, those will be on the outside, and those can form hydrogen bonds with the water in the surrounding solution, and this whole structure ends up being a sphere with a hydrophilic outside and a hydrophobic inside, and these little spheres are called micelles. A real-life example of micelles at work is dish soaps and detergents. So they use these amphiphilic kinds of molecules, the non-polar hydrocarbon parts of them that are hydrophobic interact with, for example, grease and other stains in your dishes or on your clothes, and sort of pull them together into the center of a micelle. And then because the outside of the micelle is hydrophilic, you're able to wash away the whole thing in water, and that helps you clean your dirty dishes. Other types of biomolecules that are amphiphilic because of their shapes tend to form a slightly different, they have a different solution for how they want to be most happy in water, and they'll form what's called a lipid bilayer, and that's shown on the bottom of this figure. In the lipid bilayer, the hydrophobic tails do also hide in the center, and then the polar head regions, which are hydrophilic, are on the outside, and they're what interact with water. So as part of a cell membrane, you might have the outside environment on one side, which is aqueous, and then on the inside you would have the cytosol, which is also aqueous, and so you need those polar head groups that are happy to interact with water, sort of on those two edges, and then the center can contain those more nonpolar hydrocarbon tail regions, and that would have, and you have two layers. You have one polar head group with the nonpolar tails on one end, and then the nonpolar tails and the head groups facing the opposite way on the other end, and that is why it's called a bilayer. It's two layers of amphiphilic molecules, as opposed to the micelle, which is sort of a single layer. You have just one set of molecules with all of their tails in the center of that sphere. So that brings us to how solutions of water might behave with various solutes that are in it. And so we want to consider how solutions might behave when they're mixed together with other types of solutions. So here we have an example. We have a semi-permeable membrane here, and it contains this concentrated solution that's shown in purple with a whole bunch of solutes in it and other substances that's surrounded in the beaker with water. And this membrane is only permeable to water. So now water has this problem, right? So on the inside of this membrane, you have water with a whole bunch of stuff in it, and you have on the outside of the membrane just plain water. And overall, the solution wants to kind of even itself out. That's sort of part of what we've talked about with entropy. In general, systems want to be at equilibrium, and here we're not at equilibrium. So because this membrane is water permeable, water will end up going from this outside portion through into the water permeable membrane to try to sort of dilute out this concentrated solution that's inside of it. And that movement of water is called osmosis. But if you were to exert pressure on that membrane to force some of the water back out of that membrane, that can still happen. You just have to exert pressure from the outside. And that pressure that tells the water to move, that's called osmotic pressure. So once again, osmosis is the movement of water. So if we want to talk about osmotic pressure in a more mathematical, sort of systematic way, we can use this equation where we have capital letter pi, that's the osmotic pressure, equals I times mRT. So I is the Van't Hoff factor, and that represents the number of molecules or ions that are produced when a substance dissolves. M is the molarity. Molarity is a concentration, which you should hopefully already know. That's the moles of solute in 1 liter of solution. R is the ideal gas constant, which you've probably seen before, and that's equal to 0.0821 liter atmospheres per mole Kelvin. And finally, T is the temperature, which is in Kelvin. So using this idea of pressure and movement, we can also think about another similar example to what we saw before with osmosis, but here we're looking at dialysis. So the difference, some things are similar here. We have a big beaker with our solvent, which could be water, could be something else. And then we have a membrane that contains a more concentrated solution. But here we're using a dialysis membrane. So dialysis membranes are permeable to water, but they also, their pores are maybe a little bit bigger. So then that membrane we saw before with the example of osmosis, that membrane was only permeable to water. A dialysis membrane, depending on the size of the pores, can be permeable to larger molecules, including some ions in your solvent. So this can be very helpful if you have multiple types of molecules within your concentrated solution on the inside. So for example, here we have little red dots, which are smaller molecules that are dissolved in the solution, and then we have larger purple dots, which represent larger molecules. And so this dialysis membrane in this example has pores that are large enough for the red solutes to move through, but not for the purple ones. So once the dialysis reaches equilibrium, now we have a case where a lot of the red solutes have moved out of the dialysis membrane to sort of go to equilibrium. They are now the red molecules are less concentrated inside of the dialysis membrane, whereas all of the purple molecules, which are too large to fit through those pores, they're still all stuck inside. They cannot leave, even though they would want to, because they are more concentrated inside the dialysis membrane. So the dialysis is actually a handy method that we can use in the lab to try to purify a mixture of molecules that are different sizes. We can trap our large molecules inside the dialysis membrane while allowing the smaller solutes to move out. And if you continue to swap out the solvent in the large beaker with sort of fresh solvent that doesn't contain solute, you can draw out more and more of the small red solute molecules into the outside part. So one sort of real example of osmosis and osmotic pressure that we are going to talk about here is red blood cells. So red blood cells in an isotonic solution that has the same concentration of solvents inside the cells and in the solution surrounding the cells, those cells are sort of what's called isotonic. There's movement of water is allowed in and out, but overall there's no net movement of water. It remains equal, the same. So the cells remain the same size, they retain that happy little donut shape, and the cells can perform their function. That is very different when you put those cells into different types of solutions. So if you put those cells into a hypertonic solution, A hypertonic solution is more concentrated solutes in it, so the water that's inside the red blood cells has this osmotic pressure to leave the cells to try to even out the solution on the outside to the inside of the red blood cells. So as a result, you have this net movement of water leaving the red blood cells, and the cells can shrivel up and in general can't perform their function as well because they've lost their shape. The sort of opposite of that is red blood cells in a hypotonic solution. So a hypotonic solution is less concentrated solutes than we would normally see inside the cell. So as a result, the water outside of the cell tries to move into the cell to again try to equal out the salts and other solutes in the solution. And so because of this pressure, the water moves in and the cells become overfilled with water and they can actually burst open, which would clearly kill the cells. And so that is another big problem for your red blood cells. So it's very important for homeostasis to stay alive, for your red blood cells to always be in an isotonic solution. So with that, now we've covered the basics of the physical properties of water in Chapter 2, and you're ready to answer the physical properties of water practice questions. Thank you.